Next, we have Till Hoffman, who does work at the Harvard School of Public Health. He's doing work on low-cost surveillance tools, which includes wastewater surveillance, which he's going to talk to us about today.
Perfect, thank you. So this is very much about the beginning process of wastewater surveillance again, as Andrew was discussing. So yeah, we want to get interesting information out of this really, really messy stuff that we're collecting. And I think as Jeremy was highlighting, there are many, many more components to this problem than just shedding. You know, what about dilution? What about collection? What about the actual assays? But this talk is very much about the first part. You know, what goes down the drain? Because we need to know what goes down the drain to be able to interpret these data. So yeah, a few questions we might want to ask is, does everyone really shed SARS-CoV-2 RNA in their feces, or is it only a subset of people? And that's interesting because we might want to adjust our estimate of prevalence, although that is very hard, to account for only some people shedding. Or it might tell us something about that some people have enteric infections through SARS-CoV-2 and others don't. How many gene copies do people shed? That's, of course, something that we need to know to be able to estimate prevalence. And that's what the shedding hub is all about. And then one big question is, how is viral RNA shed over time? Because that tells us something about how effective wastewater-based epidemiology can be for being a leading indicator. So what data might we have? This was work from 2020, so it is very much chaotic and panicky. And at the time, we only had 3 data sets. So these were all from early 2020. What we've got is the gene copies per milliliter of stool. And all the circles here are quantified samples. And the horizontal lines are the limits of quantification. And all the little crosses underneath are things that we couldn't quantify. And we want to make sure that we're really modeling the whole process, the whole generative model, because what does a negative sample tell us? It doesn't tell us that there was no RNA in the sample. It just tells us that the concentration was below what we could detect with the assay. So what might a model look like? We, of course, have patient-to-patient variability. So I've got these kind of 3 colors here representing different patients. We've got this blue patient at the bottom who doesn't shed very much, and we're collecting samples relatively late in the infection course, and they're all negative. Now, does that mean that that patient doesn't shed? Not necessarily. It just means that we collected samples at a point where the RNA concentration was below the limit of the assay. And then the green patient here, for example, has very high concentrations. We collected samples relatively early, and all of their samples were positive. So we want to build a model, formalize this. There's only a few of these. So we have this mu-I, which is the individual level effect for a patient. So that tells us, compared with the baseline of the average member of the population, how much does this person shed? And we use here what's called a generalized gamma distribution that has a location parameter, a scale parameter, and a shape parameter, which tells you about the tail shape of this distribution. Now, we could have used a log normal distribution or a gamma distribution or your Weibull distribution. Pick your distribution with positive support. That is your favorite. We use this one because it's a bit more flexible, and we'll get back to why that is important. So that was the patient model, and now we'll have a look at the individual sample model. So we're looking at the density here of the concentration of SARS-CoV-2 in our sample. And if that concentration is above the limit of quantification, which I've called theta here, then we just have a density, again, a generalized gamma distribution centered on the individual level of shedding of that individual times some sort of shedding profile. So this G here is just how the shedding vary over time. And for the time being, we'll assume that that's shared across all patients. Of course, we might again have variability across patients, but we didn't have enough data to drill that far down. And then again, we have this sigma and q are the scale and shape parameters for the individual variability within a patient. But we might not always have samples that are above the limit of quantification, right? So all we know is that the concentration was below the limit of quantification. So the capital F here is the cumulative distribution function. It's just all the mass that's in the tail of this distribution. So that's the basic model. Before I move on, anything I should clarify? I'll take that as a no for now. So coming back to why do we care about these generalized gamma distributions, right? It seems like a bit of a technicality. So this is data from one of the early studies by Wölfel and others. And this is the fecal shedding data from the first patient in their study. And I've just added a little bit of jiggle here so you can see the individual samples, but we've got kind of just above 10 to the 2 to 10 to the 7. So let's fit distributions, right? We'll fit a log normal distribution, a gamma distribution, and a Weibull distribution exactly to the same data. You get completely different fits. And that's just because we made a commitment to the shape of the distribution, the functional form. And that has very important consequences. So if we look at the predicted mean after we fitted these distributions, for the log normal distribution, we get 1.4 times 10 to the 7 gene copies. Whereas if we'd used the gamma distribution, we would have got 2 times 10 to the 6. So it's almost an order of magnitude. So if we added another sample at 10 to the 1, so a smaller sample, the sample mean goes down, we'd actually get 4 times 10 to the 7 as the predicted mean for the log normal distribution. And that's because we get heavier tails to account for that extra dispersion. So you have this very counterintuitive result that by adding smaller measurements, you get a larger predicted mean. And that's why we want to really learn about the shape of these tails. So this is the same data as before, but now with a shedding profile fit. This is just an exponential shedding profile. This is of course unrealistic because if you go to 5 days before symptom onset, we'd predict that you have some enormous shedding. We'll get back to that in a minute. But the shedding half-life here, this is not the degradation of material once shed, but it's how quickly does the amount of RNA that's shed decay over time. So it's about 1.5 days, and that means that over the course of 5 days, you're going to lose about an order of magnitude of RNA concentration in your stool samples. So that explains some of these challenges that we've had, for example, where if we take samples from aircraft, sometimes the data suggests that everyone, or maybe more than everyone, on this aircraft is infected with SARS-CoV-2. But that's because they're probably in this regime here, right? They're early in their infection course. Maybe they don't have symptoms yet. Maybe they're asymptomatic. But all the clinical data is later on in the infection course. So using some of these modeling techniques, we can reconcile some of the wastewater data and some of the clinical data. So here we've used a gamma shedding profile as Jeremy did. It's one of the classic ones. And we said, actually, we're going to introduce another parameter, which is when does shedding start? Because we don't know. It doesn't happen at symptom onset. It doesn't happen right when someone gets exposed, but somewhere in between. So the important thing here is that it could be any. Right? We don't know. We don't have data that tells us when shedding starts. And there have been publications that tell you shedding peaks at this time and at this value, but we don't know because we don't have the data for it. Now, interestingly, the tail here is consistent with an exponential, but you might argue, well, the gamma distribution has an exponential tail, so that's why. Another one is, this was kind of from polio data. This is an exponential rise and an exponential decay shedding profile. Again, it looks very similar, but again, we can't identify when shedding starts or where it peaks. So we have another variant. We wanted to know, does everyone shed? So we can say the likelihood of our data for a patient that has all negative samples. Of course, if there's one positive sample, they definitely shed. But if there's all negative samples, it can be either that with probability 1 minus rho, they never shed, or with probability rho, just they shed a very low amount. And if we fit that, we actually find that this rho is consistent with 1, meaning that the data that we have are consistent with everyone shedding. And that the negative samples that we observe are actually just a consequence of the limit of quantification being high enough that in the later stages of shedding, when people come to hospital, because you don't get stool samples early on in the infection course because people don't like collecting their own poo, we can actually assume that everyone sheds. And that again comes to this point of the viral RNA in wastewater is often higher than we would have expected based on clinical data from hospitalized patients. So I think modeling is essential to constrain the shedding because there's so many different components. There's these limits of the assays, there's the tail shape of these distributions, there's patient-to-patient variability, and we really do want to capture that. I've mentioned there's a few times we can kind of reconcile only shedding and wastewater-based surveillance data, and the data are consistent with everyone shedding, but to different degrees. Some people just have very low shedding rates. So what's next? We do want to expand the shedding hub. And I think the interesting thing there is we do want to go beyond just infectious diseases. So for example, if you're exposed to benzene, there are going to be metabolites in your urine. Can we go towards, for example, looking at environmental determinants of health by looking at metabolites of toxins that you might be exposed to? We have more data now, so having a non-parametric shedding profile could be interesting because, again, we don't have good information on what those profiles should look like, and we should just learn them from the data, And we'd love to have random effects. We just had random effects for patients, but there might be variability for demographics, as we've seen for disease severity, for example. Different studies will use slightly different methods, so there's probably going to be variability there. Some studies use, an N gene target, some use E, some use RDIP. We're going to get different results, so we might want to look into that. Different viral variants might have different shedding. That's definitely something that we've seen in nasopharyngeal samples. Does that hold in stool as well? And you can keep going. Right? There's so much variability in these data, and whatever you might be interested in, hopefully we can get the data together in the shedding hub. And if you have data, we'd love to have it. And I think that's it from me.
So like, what about the next step? Like, you gave the example of the plane, right? And we see a very high viral load in the plane stool. And that could be, based on your model, a few people early in their course, or it could be a bunch of people late in their course. How have you thought about how to best actually translate these shedding profiles you're getting to how we should think about the numbers and the uncertainty in an individual measurement, I guess?
Great, thank you. I think some of that uncertainty is fundamental in the sense, for example, what Scott mentioned regarding shot noise. If there is one super shedder, we won't be able to distinguish that probably ever from 10 people shedding at an order of magnitude less. So I think some of that is kind of fundamental to just the way this process works. I think in the setting of the airplane, it's actually very well controlled. So maybe the uncertainties there are more on the limit of the fundamentals. But I think in kind of well-sewered environmental surveillance, there are probably a number of things that we can do of estimating dilution factors, having a look at residence times to get at the degradation, exploring different sampling techniques. Where should we sample? Should we sample in network, at the influence? Should we sample sludge, etc., to minimize some of those uncertainties?